Oil and water just don't mix. It's like they're polar opposites. And from a chemistry perspective, well, it actually is about polarity. This is Real Chem. Oil and water are a great example of the impact of polarity associated with different kinds of bonds. You may already know the differences between covalent and ionic bonds, but the reality is that these bond types actually lie at opposite extremes of a spectrum, with many intermediate bonds between them. Let's explore this. The spectrum from covalent to ionic bonding is all about how the two atoms involved in the bond share or fail to share electrons. It's like there is a tug-of-war happening between the two atoms involved in the bond. The strength an element brings to this tug-of-war is called the electronegativity. The difference in electronegativity, delta En, or change in electronegativity, between the two atoms determines who wins. An example of one end of our spectrum is the pure covalent bond of Cl2. Since both atoms are chlorine atoms, the change in electronegativity is 0. Our tug-of-war is an even match, and the electrons are shared equally between the two chlorine atoms, giving each atom a charge of 0. The other end of our spectrum is the ionic bond, like sodium chloride. The electronegativities are 0.9 for sodium and 3 for chlorine, giving a change in electronegativity of 2.1. It's like a tug-of-war between my grandmother and a sumo wrestler. My grandmother would win. But in this case, the chlorine wins nearly all of the available electrons, meaning that the single valence electron of sodium is stolen away by the highly electronegative chlorine atom. The loss of an electron by sodium gives it a charge of +1. The gain of the electron by chlorine gives it a charge of -1. Pure covalent bonds and pure ionic bonds are at opposite ends of our spectrum. So far, fairly straightforward. So what happens in the middle of the spectrum? Consider HCl. Chlorine is more electronegative, 3.0 versus 2.1, so it will win the battle for electrons. But the electronegativity difference is not that large. The change in electronegativity is 0.9, so it's not winner take all. Instead, electrons are shared between the hydrogen and the chlorine, with chlorine getting more of the available valence electrons. As the chlorine has a bigger share of the negative electrons, it is slightly negative. Its charge is not a full -1, and we show this as delta minus. Similarly, the hydrogen has a smaller share of the negative electrons. It is slightly positive. So we show this as delta plus. We call this a polar covalent bond. Let's explore the spectrum more by pitting fluorine, the most electronegative element with a value of 4, against a series of competitors. At the far right, we have a change in electronegativity of 0 for F2, a pure covalent bond. The percent ionic character is 0. The percent ionic character increases as fluorine is paired with other atoms with increasingly lower electronegativities. So oxygen, nitrogen, carbon, boron, beryllium, lithium, sodium, potassium, until on the far left, we have cesium fluoride with a change in electronegativity of 3.3. Cesium is 0.7. The change in electronegativity is so large, we have nearly a pure ionic bond with 92% ionic character. So at what point should we say we have switched from a covalent to an ionic bond? This is a bit arbitrary, but the change in electronegativity of 1.9 is commonly used. Anything beyond 1.9 and we say we have an ionic bond. The arbitrary nature of the change in electronegativity being 1.9 arises from trying to put restrictive labels on the amazingly beautiful phenomenon we call the chemical bond. So, coming back to that old adage, why don't oil and water mix? Well, in short, It boils down to the fact that they lay on our spectrum in very different places. If we understand this, a lot starts to make sense. So explore and remember to have fun.